Ready for circuits? Yeah. Last new material, right? Hallelujah. Do you have any questions about anything before I get going?
On the final exam, do we get like a paper like the other exam?
Yeah, on the final, it's just same format as all the others. It's just 2 hours, more questions. And you'll have to cram it all because there's more material. But yeah, you can still have one cheat sheet, your calculator. Yeah. Final again is Friday, this Friday, at 10:30. So it's a little sooner, from 10:30 to 12:30. So it overlaps this time slot, but it starts at 10:30. If you forget, it's on the university's webpage. It's on my calendar. It's on WebAssign. If you didn't know about it by now, I don't know. But yeah. And since it's that important, I'm going to double check. My calendar, final exam. Yep. Friday, 25th, 10:30 to 12:30, right here. Anything else? Yeah.
When will we get our grades for a superhero paper?
I'm shooting for Wednesday, but if I don't, it'll be the final. Before I never see you again, I will get them to you. I am enjoying them.
How has it been so far, the average grade?
On the papers? Most people are doing well, yeah. Most of the docking of points is because people didn't follow instructions, didn't include things, or did it wrong. But yeah. But no, what they've come up with has been good. That's the part I like. Okay, well, that's a clicker question you. I chose 4. All right, first one, the electric charge will flow in an electric circuit when? Under which of those conditions? It's in there somewhere, right? Ten, 9, 8, 7, 6, 5. He found it. I'll wait for him. 4, 3, 2. Now you can read it. Tell me when you got it. Did you get it? Okay. All right, most of you think it's B. Very good. A potential difference exists. That potential difference is a difference in electric potential. That's what we're talking about, electricity. Electric potential, another word for it is? Voltage. So here's where you have a difference in voltage. You know, it might be 9 volts over here and 0 over here, or 120 and 30. If there's a difference, there's going to be an electric field established, and that's going to make the charges move. That's what pushes them around. Whoop. Oh. Okay. If you double that voltage in a circuit, what else do you double? Your hint is Ohm's Law, which we'll review again today. Oh, heck, I'll even write it on the board. or rewritten as nine, 8, 7, 6, 5, 4, 3, 2, 1. All right, most of you think current. Some of you think you're going to change both of them. Okay, the majority wins. It is current. Just for this part. If you have a circuit, by doubling the voltage, you're not changing this actual circuit, the components in it, so you're not affecting the resistance. That's what the circuit's made up of. If you change the wiring or add or subtract light bulbs or something, that would change the resistance. So only the current gets doubled for a certain circuit. Think of it this way too, if you chose both. If you double the current and you double the resistance, they're both doubled, the voltage should be quadrupled. But for a given circuit, you're not messing with the resistance. So these interplay. Or the way I introduced it, the amount of current that flows, what determines whether it flows is if you have a difference in potential. If there's a voltage across some resistance, then that push, it'll establish an electric field and cause these charges to flow through that resistance. So if you push twice as hard by doubling the voltage, you'll move twice as much current, charge. Okie doke. To receive an electric shock, there must be what? Your clue is, I hope you get this one after the last two questions. There's a theme running here. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Most of you see. Very good. Again, none of those charges will start moving. There'll be no current unless there's a difference in potential across some part of your body. That's how you get a shock. You realize with that then, if you grab onto a high voltage wire over here, and you grab onto the same wire, like right next to it, it's essentially at the same potential there. It's like, it's 1,000,000 volts! But this is 1,000,000 volts too. So you think you'd get shocked? No, not likely. What if you're grabbing onto the 1,000,000 volt wire while you're touching the ground? What potential do you think the ground's at? 0. It's a big charge sink, so it can supply or it can neutralize things easily. Well, now you'd have a huge potential difference across yourself, and that would cause the charge to flow through you. Not a good idea. Okay, I have one more. Any questions? Concerns? While we're on this one, electricians learn this. If you ever have to mess with electricity in your house, they always teach them, do it with one hand. They often put one hand behind their back, or grab their belt while they're working. Why? Let's say they accidentally hit some high volt electric potential in one spot. How will the current flow across their body? Zzz. Where's it going to go, you think? We're a conductor. Yeah, through your arm and into the floor. What if you're messing with two hands? Where could it flow? Yeah, right through your heart. Not a good idea. So if you only use one hand, at least maybe it won't go through some vital organs. You're even safer if you insulate yourself, but all right, last one. What travels at about the speed of light in an electric circuit? lot of people think when you flip a switch, something's cruising near the speed of light. Something does, but other things don't. Hence, it's not D. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Oh, you guys have no idea. All right, talk to your neighbor and see how this turns out.
Yeah, at the end when we see it, just because, were you here when we did that experiment with the last time? What did you guys find? Yeah. So that basically we all like got into a circle and touched each other and like the charge and it was because of the electric.
So what's the difference when they talked about DC and AC in the flow?
That's my first demonstration I'm going to do after this one, yeah. DC versus AC. That's my intent. Sometimes I derail myself, but it's right here. You make me do it before class ends. All right, revote. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Meh. Oh, you guys did sway each other. Yeah. Was it correct? Got my work cut out for me. No, the majority's right now. Electric field. Unfortunately, it was just over half of you, though. So about half of you are still a little befuddled. So you can put your clickers away. Let me turn the lights up. So, where's the source of charge in a circuit? What? The material. It's already there. So the circuit's already full of charges. So one thing I like to think is it's not like they come from the battery or the power supply or out of the outlet. They don't just magically flow, whoosh, go through you and return. They're already there. What gets them moving? We've discussed this already today. What gets the charges moving? They won't move unless there's an electric field, which is caused by separation of charges. There's a higher electric potential in one spot than another. Voltage difference. So yeah, an electric field is established. That's what's established at the speed of light. If you get confused, think back to light, visible light, radio waves, microwaves. They're electromagnetic waves. They have an oscillating electric field and an oscillating magnetic field. That travels at the speed of light. So the speed of light, or electric field, is established almost, for all practical purposes, instantaneously. And so all the charges instantaneously feel that and start marching in sync. I like the analogy of the book. They're like soldiers. Ready, march! And you all start moving together. Now, let's talk about the two types of circuits, though, because the movement is slightly different. Those charges themselves are moving at a snail's pace. Almost literally. They're slow. The actual charges themselves don't have to move that far or that fast to still have current. We still like to think the electric field's established, so they start moving, and that gets them to go, okay, but they're not as fast as the speed. No, they're actually quite slow. All they need to do is just move a little bit. Actually, they can just wiggle, and you still have electricity, as long as there's motion. So the two types of circuits, to help explain that a little more, are AC and DC. DC is direct current. That's like with a battery, like this, car battery. The current, which is just the flow of charge, so it's actually technically incorrect to say, and we do it all the time. I still succumb to it. Saying the flow of current is redundant because current is the flow of charge. What's moving are the charges; they're wiggling. In direct current, they flow in one direction, and your book calls it drift current. The electric field again is established at the speed of light, but the charges start marching slowly in one direction. And which direction do you think? If they're electrons, they're attracted to the positive side. And where the electrons are missing, deficit, it's left net positive. So positive ions would go towards the negative side of a battery. That's direct current. But they're just kind of inching along. Do. Alternating current is what it is. It alternates. It changes direction. So the electric field is pushing them one way, and then the other way, and then back, and back, and back. And does anybody know how fast that occurs in the United States? What the frequency of our electricity is? The frequency is 60 hertz. You know what that is now. That means it changes direction 60 times every second. Cycles per second. Yeah, so it does that. Well, if you start pushing a charge this way, and then back this way, and then back this way, in alternating current, the net effect of an individual charge, it goes nowhere. I mean, it's moving around, but kind of like this. Gets pushed, and then it runs into other particles too, right? That's resistance. So they get knocked, and so it's kind of just doing this. And alternating current, and then ultimately it goes nowhere. Direct current's more like, but over time, it kind of drifts in one direction. Does that make sense?
For your direct current, you said you have electrons going this way and the positives going that way. So, which way is the current?
Yeah, historically, Benjamin Franklin came up with the terms, in essence, positive and negative to the proton and electron. And historically, it should have been the other way around, but nobody changed that. They messed with Pluto, but they didn't decide to change protons and electrons. Think of this: if you got an atom and an electron's free to move around, the electrons can go one way, but this is left net positive. It's like a hole. And sometimes there's positive charges that can flow. If they're free and not attached, they can move the opposite way. And so when we say current is flowing, it's actually the positive charge we're referring to, not the electrons. Just as an example, this circuit I've drawn up here, we're going to get to. This is like the battery. It's this icon for a battery. It's voltage. Current flows out of the battery. See, I said it. Current flows. Charge flow is the electric field's in this direction. And so we say the current goes like this, the way I've drawn the arrow. That would refer to the positive charges. Technically, the electrons are going the other way, which is kind of weird. But that is what's happening since you asked. Do you have a question?
Yeah, I was wondering practically, how do we use AC current and DC?
Practically, they can have the same effect. You can store energy by separating the charges, and then making them move, you can do work. And a lot of things don't care if it's AC or DC. So why the difference? That's a loaded question. Biggest reason that we don't have time, we ran out of lectures, is alternating current. It's changing direction, and a change in that electric field can create a magnetic field. Remember our light waves, they go hand in hand. And transformers ultimately work because of AC. You can step up voltage or step down voltage. And current for that matter. If the voltage goes up, the current goes down, because you got to keep things conserved. And transformers only work with that change, which is only in alternating current, AC. And that helps us transmit power to the world. DC, it was more impractical in the day. They've come up with ways now, but we're all on AC. So there was a big war. You can read about this historically between Thomas Edison and Westinghouse, who had Nikola Tesla on his side. And one wanted DC, one wanted AC. AC won out.
So if we wanted to just power this room and without that power source powering anything else, DC would work?
Yeah, essentially DC would still power this room just like AC. Certain appliances are built to only work on one or the other. If they have a transformer in it because they need to step up or down the voltage because it needs to run on more, then you know it needs AC. But lots of things, it's converted to DC. When you have things like this. This converts the AC coming out of the wall to DC to power this. Because it doesn't run by switching directions. And vice versa. Some things, just the way they're built, don't. So let me show you a demonstration. This runs off of AC because it's plugged into the wall outlet. Guess they don't need that. So I have an LED that it's going to power. Turn it on. And what color is the LED? Kind of yellow-orange. What makes up yellow light? Green and red. Well, that's what's inside this LED. There's two of them. And the way they're wired is, and I actually forget which is which, but it doesn't matter. The idea is, let's say red is when the electric field's flowing in one direction, and green's when it flows the other way. So half the time the red's on, the other half the green's on. That's alternating current. Goes one way, red. Goes back the other way, green. Red, green, red, green. When you separate them, you can see the two. See that black spot in between the red and the green? That's where the power company's gypping you. You're not getting any power. Now, am I worried about that? No. But is it true? Yeah. This is what alternating current looks like. Here's DC. Let's do AC. Let's see if you have voltage versus time. And voltage versus time. All right. With DC, it's like, 12 volts or something. There. It's fixed. It doesn't change. So everything goes in the same direction. Alternating current changes direction. So it goes up, it increases, comes back down. Goes the other way. Positive, negative. And it alternates. And this stuff from our wall gets up to 120 volts. Well, we say it's 120 volts. But it's changing. So it's not 120 all the time. It actually can get up to about 170 volts here, positive, and down here negative 170 volts. And it's a sine wave. It oscillates between positive 170 and negative 170. Ramps it up, and they start accelerating one way. They slow down, but they're still moving positive. And then there's zero. See these spots where there's zero? That's when there's no potential difference. That's the black spots. I mean, for a brief second, you're not getting any power. You don't have to worry about it. So here moves it one way, here moves it the other. We use 120 because we got to plug something into our formulas, when we got to, how do we measure this if it's always changing? Do we take the average? That's what people wanted to do. What's the average of this? 0. Well, that's not going to help us. So you don't need to know about this, but they come up with something called root mean squared. It's essentially they like flip this, square it, and then square root it back so you get a value. And what you end up with is this 120. That's the value we can use. And this alternating current would function exactly like direct current if it was 120 volts. You'd have the same power, same general effect. So it works out nice. But that's the difference. Direct current is fixed in one direction only, and alternating changes. Here the charges just kind of drift along slowly. Here the net effect is they don't end up going anywhere. They're moving, but they don't really progress. How'd I do, Emily? All right. Now, when you send these currents, you're trying to push them through various things. We talked about the resistance. Things that are really skinny, it's like it's hard to get through, that'd be more resistance, like a thin resistor. Or if it's wide, it can get through easier. When things go through, when charges try to go through objects, if there's more resistance, you're moving them around more, the charges, and the material. You move them around enough, you speed up their average kinetic translational energy, what happens to it? It heats up. You send electricity through about anything. Because of its resistance, it heats up. That's how we got the light bulb. It's like, hey, if we send enough current through this filament, it'll start glowing. Because remember, the peak wavelength that it'll give off, peak frequency, is based on its temperature. So if we can raise it up high enough and get it in the visible range that it emits instead of just infrared, we could see it and it would provide light. So here's a little example. They used to make fuses like this too. Say you put something like this, a little thin piece of wire, or it's in a light bulb, in a circuit. Say it replaced this. If the filament broke, whoosh, do you see that there's no electric field from one side to the other? And that would stop your current from flowing. That's the effect of a fuse. You didn't want light bulbs to break, though. He had a hard time finding the right material so that it would glow. That's why he put it in a glass envelope and lowered the pressure quite often, or changed the gas inside so it would burn longer before it would break and go out. So this I have connected here. It's cooler in the dark so we can see some glowing. Let's dim it a little here. Zoom in on this guy, because I'm going to put a big potential difference across it, try to cram the charge through it, and you'll see it heat up. You ready? Oh, double safety precaution. This could kill me, so let's plug it in now. Okay, now flip the switch. There, light bulb. Oh, fuse. Okay. That's all there is to that. That would make a very, very bad light bulb. But, it's safe now. It just burnt the wire. Heated it up. The funny thing is that the hotter something gets, the more easily it is to allow current to flow. That's not right. The colder it gets, its resistance drops. Yeah, let me say that right. The colder something is, its resistance drops. So when this heats up, that actually increases the resistance, which heats it up even more. It's a runaway effect. That's what I was trying to say. You should understand this. We talked about interactions with sound waves and light waves. Think about it. If something's hotter, what are the little molecules and particles doing? Yeah, and we're trying to move things across it. Is it going to be easier or harder? Yeah, harder. It's like they're doing their own thing, not what you want them to do. Let the charge go across. So that thermal motion is hindering the current. So it acts like more resistance. And in general, things that are hotter have more resistance. Things that are colder have less resistance because of those interactions. But it's a runaway effect here. It heats up because it has resistance, but now it's hotter. It's got even more resistance. And as it burns away, it actually gets thinner, which that makes even more resistance, harder to get. And yeah, that's why the thing eventually just burns apart and falls away. Let's do this one. Let's burn some more things. Everybody should know this. So let's do it safely in our lab, right? Our lecture. So I have a GFCI rated circuit here so I don't accidentally fry myself. And I'm going to take some pencil lead and stick it across what I call this suicide cord. Did you guys ever wonder why there's 3 prongs? Today is the day. Here they are. Typical is green, black, and white. The electricians are supposed to have a consistent color code, but I wouldn't ever trust them. Here, the black is called hot, the white is called neutral, and the green is called ground. What's that mean? Well, the black is hot. That means it's going to have the high voltage on it, 120 volts on this one. The ground is green. That's probably what you think it is. It's grounded. It's like you stand on there with a big sink, so it's 0 volts. So there's a 120 volt difference between the black and the green. So if you touch this one and this one, you just electrocuted yourself. Let's do that with the pencil lead. We're going to give it a path from black to green here, if I just set it on there without it falling apart or rolling off, stay. There. So I've shorted it out. Let's plug this in. That's plugged in. It looks like it's on. Turn this on. You ready? That would have been you. So you don't touch that. That's why you teach little Timmy not to stick the fork in the outlet. Now, black is hot. White is neutral. Neutral is supposed to be 0 volts. It's supposed to be at what is the same as ground. So there should be 120 volts difference across those two. Let's see. Plug it back in. It tripped the breaker. There we go. Ready? I didn't even see where that one went. The goner. So, what do you think will happen between ground and neutral? We've done hot and ground. By the way, this one's the ground one. One of these is hot, so we did that. That's bad. We did hot and neutral, the other side. Well, that's bad. What if we do ground and neutral? That'd be the white and the green. What do you think? Is it going to go vroom? All right, on, plugged in, ready? Nothing. Nothing. You could touch those two. I don't encourage you to go trying this all out at your house, especially because the color could be different for you. But it is true. Between, or it's supposed to be, if something's wired correctly, hot, or neutral and ground should both be at the same voltage. If there's no difference in voltage, there's no electric field. If there's no electric field, no charges flow. And we like it safe if it's 0 and 0. But even if it was 120 and 120, nothing would flow unless you gave it a path to a different voltage by touching ground, by standing on the floor. So see, now you know what this is. You have to have a wire going to the device and a wire coming back. You have to at least have two to have that potential difference so that the electric field is established. But don't think of it this way. When you plug this in, whoosh, charges flow out of the outlet through this side. Whoosh, they go to here and they need a path back, so they come and flow. No. The charges are already there. We've established that. It's just the electric field that sets up at the speed of light, and then the charges start flowing.
Why do they need a neutral?
The neutral, safety mostly. You want that grounding. Most things, you only need this. And in, like my house, for example, most of the outlets don't even have a ground.
So it's like having two grounds.
But this is grounded. Here's a perfect example. I had something out here once, and it electrocuted me. I plugged it in. I was resting on. Plugged it in. Ow! What the? It wasn't wired properly, or it breaks down. If you got something plugged in and you're bringing hot in and a neutral out, and somehow that the body of the appliance is not at 0 volts, and you touch it, well, there's a difference between it and you, which are touching ground. And so current flows, and you're shocked. So quite often, too often, 120 volts, the power gets into your device, and somehow it leaks out where it goes where it's not supposed to because there's a bad connection, or it's the case is not properly grounded. And so you got a live 120 volts there. And if you touch it somewhere while you're at ground, whammo, you get shocked. So all cases should be properly grounded. Let's say it's not. If it's plugged in like this with 3 prongs, you know it's grounded. Unless they just totally built the whole thing wrong. Because the neutral is trying to get the path back, but that neutral is attached to ground, or it's supposed to be. These GFCI rated circuits are clever little things. What they do is if current flows where it's not supposed to, like through me, say I get in this circuit, then current is drawn off through me. And this notes the difference. So it's like monitoring how much charge is flowing through it all the time. And if you go into the circuit by dropping your hairdryer in the bathtub, right, you see these a lot in the bathtub because where water's at. If charge goes where it's not supposed to, this senses a drop in that current, and it'll shut itself off and keep you from being fried anymore. Actually, whenever the pencil lead went, it drew too much current, and I had to reset this each time. But it's a safety feature for me. And you know what? It's warm too, because that's a lot of current flowing through this wire. Let's do a circuit. We don't need that. Here's our battery. I got a resistor here. I'm going to send the current through some resistance because I want to limit how much current flows out of the battery. I don't want to fry these light bulbs. So this is like my power source. And what I'm going to do is I'm going to have one come off the positive part of the battery and one come off the negative. They can't touch each other. If these were to touch, it'd be like that. Because there's a big potential difference here now. So I won't bring these together and make sparks. It's not good on the battery. But let's send it through a resistor. That one there. And this one here. And we have a simple circuit. That's like this with just one light bulb. We did work to make the battery. Charges are separated. We got an electric field on the two ends. Think of it this way. This side, by convention, is positive. That's negative. When I flip the switch, this has no switch. This side is all at the same potential, and it gets to the light bulb. Without these guys, this side gets all the way to that side. So it hasn't had to do any work until it gets to the resistor. And across the resistor, it feels that difference in voltage, right? That's where you play Ohm's Law. You want to know how much current flows through that resistor? Well, let's I don't know the resistance. Let's make it up. Let's say the battery's 12 volts. That's right. Let's say this resistor is 12 ohms. And I haven't told you that yet. That's the unit for resistance. Ohms. It's the Greek letter omega. Okay, use Ohm's law and tell me what's the current flowing through that one resistor. You got 12 volts across it. It's 12 ohms. You get 1 amp, which is short for ampere. It's a French guy's name. You've probably heard of amps. That's the current, the unit for current. Flow of charge. Remember, that's Q over time, the flow of charge. So yeah, there'd be 1 amp of current flowing through that resistor. What if I connect the second one up in series with it? Let's add a second one. What's the resistance now? It doubles. It has to get through both of them. So the total resistance would be 24 ohms. How much current will flow through these now? A half. And look, they even look dimmer. Yeah. The current's the same in a series circuit. The current's the same in a series circuit. That's important. The current's the same in a series circuit. I'm going to even write it. Current is the same in a series circuit. Because think of the water through a pipe. In order for the water to get to this light bulb, it has to go through this one. Whatever makes it through this one gets to this one. Anyway, the current has to get through both. They're in a line. It's like we made the pipe longer. We've increased the resistance. So for the same push, you can't push as much charge through. But they both get the same amount. It's just less now than when you just had one bulb. What if we add a third? What will the current be with 3 bulbs in series? It'll be the same in each bulb. But what will the actual value be through each bulb? Good. Some of you are reasoning this. Some of you are sitting there waiting. What's the total resistance? 12 plus 12 plus 12. 36 ohms. That's how you do this in series. The resistance just adds up. The resistors add up. You can think of it like this. Resistor 1 plus resistor 2 plus resistor 3 equals the total resistance for the circuit. While I'm on that format, if the current's the same, then the current through bulb 1 is the same as the current through bulb 2, which is the current through... You get the idea. They're all the same current.
So is it like the total current is the same? I mean, in the circuit, or?
Yeah, it's the same everywhere in the circuit. So let's get back to what it is here. If this is now 36, because of all three, right? So this side, the electric field gets to here. Now it has to do work from there to there. That's the 12 volt difference across all three of them. 12 over the 36 ohms is a third of an amp. So this is a third. There's a third of an amp flowing in resistor 1, in resistor 2, in resistor 3, over here, right here, through the battery, through the switch, over here. It's the same everywhere in a series circuit. Yeah, in the back.
You know, if you have the blinker go out in your car, it blinks twice as fast.
Yeah, I do know that.
Why wouldn't it just be twice as bright?
Well, when the blinker, yeah, one of yours goes out, it does change it. Well, short, simple answer, the circuit's not this simple. There's other things going on. But think about that. You got them plugged in the way you want. They're happy. They're running. If one goes out, are the others still lit? In a series circuit, they're not. If I just get rid of that one, you have to reconnect. It's like there's a break in the filament there. No break? Electric field. Break? The wire. They would go out. So what that's telling us is they're not hooked up in series.
But if you took just one, if you unscrewed one of the light bulbs, the series would still go, the other two would still be on, but would the other two get twice as bright?
Well, because they're not in series, other things happen. Maybe I can answer this better when we do parallel. But something we can note is, they're staying on, so something shifted. You've like removed one of the bulbs. You've changed the resistance of the circuit. And I think you see that by changing the resistance of the circuit, which bulbs are in it, you change how much current flows in the whole circuit, and thus the other bulbs. And that's what's affecting them. Does that help for now? Might be clearer when we get to parallel. But if one goes out, there's a break. So all of them will go out in series. Okay, so you got the amp. You see how that works? What they do have to share is the voltage. So the total voltage, that 12 volts, has to be split and shared among the bulbs. So let's do an example, the one we're on. If you got all three bulbs, what do we say the current through each bulb was? A third of an amp. So the current here, well, everywhere, is a third of an amp. So you have a third of an amp here and 12 ohms. So how much of the voltage is used up across that resistor? You just play Ohm's Law. Voltage is current times resistance. 1/3 of an amp times the 12 ohms it's going across. Yeah. So there's a 4 volt potential difference across that bulb. Or you can think of it as he uses up 4 of the volts. How much does the second one use up? It's the same resistance, so 4 and 4. Well, what's 4 plus 4 plus 4? 12! That's, it always works out that way. So in a series circuit, the voltage is shared. The current's the same. Resistors add up. And if you undo one of them, they all go out. Ready for parallel? Okay, we go back to our 1. Let's add a second one in parallel, and what do you think? How do you think its brightness will compare? Okay, good. Because both see 12 volts, don't they? This rod's, say, at 12 volts, and this side's at 0, because that's the sides of the battery. So they each feel the same push. So, parallel. We've connected the switch. And so, it can get to all of them before it does any work. And then the opposite side. So there's a 12 volts difference across all of them. So in parallel, the voltage is the same across the components in parallel. What do you think gets shared? Let's add our third one. Let's see. Current comes out of the battery. I know, it's charge. This is how you think of it. Comes, when it gets to here, the electric field, what can it do at this point? It's got a choice. It didn't have a choice over here. There's only one path. This has two paths. It splits. So some current goes this way through resistor 3. And some goes up here. Some goes through resistor 2. And some goes through resistor 1. They do not have to be the same. So it's the current that's shared in parallel. But they have to all add up because that's what you started with. We can figure it out too. It's Ohm's Law. We know enough info now. How about resistor 1? What's its resistance? 12 ohms. What's the voltage across it? 12 volts. So Ohm's Law, 12 volts across it, 12 ohms, 1 amp. So the current through bulb 1 is 1. What do you think the current through bulb 2 is? It's the same resistance, 1 amp, 1 amp. So what's the total current coming out of the battery? 3 amps. You needed 3 to start with because it got split up. So you see how in series the voltage is shared, but they add up to the total? In parallel, the path can split, and so it's the other way around. The interesting thing is that the resistances do not add up linearly like in series. If you want to know, I won't hold you to this, but they add up like this. What it means is, when you add more and more light bulbs over here in a series, you're increasing the total resistance and you're going to get less current flowing. If you keep adding more and more light bulbs in parallel, you're actually decreasing the resistance, total resistance, that the battery sees. And so it actually has to pump out more current. You can see this, because if you keep adding more paths, and it has to keep putting 1 amp out, it's going to have to put a lot more out initially, right? So when you hook things up in parallel, yeah, they can be brighter, and it's really convenient because when one bulb goes out, the others don't. But realize when you hook things up in parallel, it's going to cost you more because you're drawing more current. So it's not as safe either. If you touch right here, you're more likely to have more charge flow off through you than if you touched over here. We're out of time. The book explains, there's one thing I didn't tell you, and I think I asked one homework question on it, but it's easy. Power. Power is current times voltage. That's the relationship. Basically, if you give it a bigger push for the same power, how do I want to say? You add more voltage, you get more power out. You add more current, you get more power out. That's the relationship. Power is what? How do we think of power before? Generically. Yeah, work with time. I'm hearing energy and time, rate. Yeah, it was energy per time. It's the rate at which we use energy. It's the same here. If you plugged in what these were, I'll leave the book to that. I only asked one question. But that's what it is. It's energy per time. Because you guys, when you have a light bulb, you see it says 100 watts. That's the unit. We've done that before, 100 watts. Well, you can figure that out now, because if you know current and voltage, or vice versa. Just with this one more equation. Okay. Thanks, everybody.